Thank you for joining us. I'm Charles Poe, Manager of Discrete Computation at Wolfram Research. And today we'll talk about GPU accelerated arrays. So first I will start with, a brief introduction of GPU programming and what we currently have before we dive into GPUArray, the new upcoming functionality for 14.2. And later on discuss about the different directions, and we hope this project will go through and hopefully get a lot of feedback from you. So let's first start. What's a GPU? A GPU is essentially a graphical processing unit. So it's a an electric circuit that performs some mathematical computation at really high speed. Right? So it first started with graphic computations and migrated to GPU when people find that you can actually use it for general purpose programming, GPU programming. And lately we have seen all the application of GPU, from game to AI right now. And what we hope is to be able to actually type the whole power of those GPU, which most of the machine come this day with, with GPU, and we want to be able to use them in the different algorithm and different function we have in the language. But let's first look at what we have right now. I mean, I think since 2008 and so, we actually have a package called CUDA-Link, which actually allow you to actually program, NVIDIA GPU. And lately we added, CUDA compiler tool. So I will slightly go to them and discuss a little bit what they have to offer and, what we hope to enhance on top of it. And as you see, both of package right now are just, based on NVIDIA GPUs, which are the most popular, the most, available out there. But, we hope actually to be able to cover, different GPU, AMD, Intel, and Apple methods. But most of my example will probably be around the NVIDIA GPUs. So, as I say, CUDA allow you to actually do some programming in the Wolfram language, right? And you can actually follow the usual, standard workflow for GPU programming. You first need to allocate a memory on your GPU, copy it from your CPU, and configure the thread, launch the thread, write a kernel code, synchronize your thread, and when you are done, take your final data on the GPU and then move it to the CPU, right? And this basic example of transpose kind of illustrate that, where you actually see here how these are the functions for CUDA-Link, where essentially you allocate the you load the matrix, you allocate the area, and here actually there is a kernel and a file in CUDA transport.cu, which actually CUDA function compile using NVIDIA compiler and load it, and then you have a function interface transpose found in the kernel, and then you can actually apply it to your matrix data. And when you are done, you actually have to get it back and make sure to clean and free your memory and return it. Right. So this kind of involves you to actually do, and pretty much there's no compilation of code like we think about it with the compiler now. And you have to do actually all the memory management, setting up, cleaning up, and writing the CUDA code behind. So with the new compiler, CUDA-Link was improved to actually add a CUDA compile tool, which is a set of tools that directly call NVIDIA libraries. You can, in short, think about it, as an extension of CUDA-Link, but with, direct call to actually NVIDIA libraries. NVIDIA had been working hard to actually add a lot of, software component to the, which come with the hardware, like, BLAST library and other mathematical libraries. So CUDA compile to take advantage of that, but it also set up, all the load and retrieval of data on the GPU and do the memory management for you, and from creating to cleaning up the object, the memory you have, the object you create, right? And so this is an example, really quickly brief, like you usually do. You do a function compile, you define the type. In this case, a numerical array of 32, real 32. And then you can create the matrix, transpose it, and get it back. And CUDA compile tool have some additional function, like in this case, CUDA transpose, and several other extensions to actually make it easy to actually just call them and manipulate different type. And I believe it have CUDA matrix, CUDA vector, CUDA matrix, and sparse version of them, CUDA sparse vector, and CUDA sparse matrix, right? So it's pretty much array of rank 1 and 2. And you have different type, 32 float, 64, and integer, right? 32 and 64 too, as well as complex. Right. So you have kind of a framework where you can actually write code and compile it and directly use your GPU. And as I mentioned, right, most of those hardware come with a lot of libraries, right? So NVIDIA actually work hard on that, and I think they have the largest collection there. They have mathematical libraries, they have the latest one, for example, graph libraries and machine learning and such. Right? And AMD is doing the same pretty much, and adding additional libraries, so you can actually, use the hardware you have, right? And the same for Intel, where they kind of build a uniform framework with one API for CPU, GPU, and FPGA. Right? So what we hope is to be able to type to all those software framework they have, and kind of leverage that to actually support GPU for all the function in the system, or most of the function in the system, I should say. So the plan is introduce a GPUArray, which is kind of a framework for representing array in a GPU, right? And that will be a little above the CUDA link and CUDA compile tools, right? And you will be able to do both allow you to do high performance computing, but also provide you an easy way to actually program and use your GPU. So we kind of want to hit that sweet spot of be able to do both. And maybe later on we kind of we can go more deep and see what are the bottleneck and how we can achieve that. Okay, so as I say, GPUArray essentially is a representation of an array stored in memory accessible for GPU. And here I say memory accessible, especially for unified framework like for Apple, unified memory for Apple, where you don't actually really make that distinction from a GPU memory and such. So if you're on Apple, we should be able to just refer to your array and manipulate it directly. Or if you're on NVIDIA, for example, we should be able to move the data appropriately from GPU to your CPU. So in short, GPUArray represents an array on the GPU. And what we hope is that from that framework, we should be able to extend many functions in the system, right? Starting with linear algebra, where obviously everything is around array there. Signal processing with Fourier and discrete Fourier transform, image processing, and obviously graph with representation as a sparse array, and geometry, and so on. But we also hope to support most of the GPU out there, and probably for this release we'll support NVIDIA GPUs and some pretty decent support for the Apple ones. And as we go on, different release will kind of extend it to AMD, Intel, and so on. The other aspect we want to also add for GPUArray is a multi-device, so GPU, CPU support. So in case you don't have a GPU available, or the algorithm cannot be actually written for GPU, you still want your function, your functionality, your GPUArray to work. So we are going to actually do the mix and make it work both on the GPU as well as on the CPU. If one of the situation, a GPU is not available, or there is no algorithm for for running on the GPU for the type of function we have, especially for our high-level functions. Right? But we also want at least the last item we also want is for GPUArray to be fully integrated with the compiler, right? So you can actually decide to bypass our evaluator and all the, stage you have on top level and, and directly, compile your code and work with it and, type directly get access to directly the performance code you want or you need. Okay, so that was the list of, what we hope to get with GPUArray, and let's see how we can actually do that. Or at least how, as a user, what we present to you. So one will have the symbol GPUArray, and essentially to create it, you create a data on your CPU. So in this case, I generate a random, set of random real, 20 of them, and I just wrap it around GPUArray. So what happened behind the scene is we take it, and in principle, we detect the type of GPU you have, right? And then we create the corresponding, we allocate the memory to the GPU, and then we create appropriate wrapper and all the management which is needed behind the scene. And then we return you a GPUArray object. So in this case, it tells you, I have a GPUArray object. It's made of real 64, which is kind of the machine real or I have on my computer right now. It gives you the dimension and it gives you a set of values in that array, right? So the construction should be, natural and straightforward for all the user and all that. So I may probably look at some question and answer to some right now or maybe later on as we go. So feel free to, write question on the Q&A section or on the chat. Okay. And as you may notice that in this case, we kind of don't want to emphasize, the type and, all the different representation of, arrays and numbers we have, right, behind the scene, right? Because usually when you are, on top level, right, you are usually machine real. So if you are 64-bit machine, you have real 64 or integer 64 or 32-bit. So you have integer 32-bit or integer 64-bit, right? But you can use numerical array to actually, represent the type you want, right? So if you want a float, so you can say real 32, and you will actually generate a GPUArray for that type. Or if you want a sparse representation, you can just do GPUArray of a sparse array, right? So as you know, so this kind of resolve the first bottleneck, which is the memory transfer. So upfront, we take your data with your CPU and then we move it to the GPU. And then we hope subsequently that all the operation will happen on the GPU, right? Except when there is no algorithm or where there is a failure. So that was when you're on the GPU, from the CPU to GPU. Now, when you have your data from the GPU, can you actually retrieve it and bring it to the CPU, right? So the function normal, retrieve the data from the CPU to GPU. And essentially, it gives you the corresponding representation as a list or a packed array or a sparse array or a numerical array in the, in the kernel, in the Wolfram side, right? So this is just a basic example. That GPUArray I generated from random real, I can just do normal and I get back a list, which is on the CPU side. Okay, so now let's see what we can actually do with that new object, right? And one thing as we all know, right, GPU, not everything can be implemented on the GPU, right? And usually it's a sim type programming style, so quite single instruction, multiple data, or multiple thread, right? So, and if you really think about it, it's pretty much like listability, right? You have a single instruction cosine, and you want to apply cosine to a list with 10 million elements, right? Such type of situation fit perfectly the GPU programming framework, right? And there will be several of different idioms. Maybe I will not highlight today, but which we discover can be quite useful for you to program or to use that. And we use that behind the scene to do several of the implementation on the GPU side. But coming back to the future, right? So in terms of array property, right? We have a GPU array, which will kind of pretty much just validate that the object was correctly built and copied to the GPU. And most of the standard operation you have, array, queue, vector, to take part, first, last, byte count, and dimension should work naturally. Okay. And next, now we kind of go and look at high-level function, right? So one of the first target here is linear algebra, right? And the hope is to support dot, transpose, linear solve, and decomposition, right? I won't go in detail with this. Itai will give a talk just after this talk on linear algebra and GPU computation. I encourage you to stop there and go and see what's the current state and how he's building that. The next area, it's Fourier analysis, and obviously for signal processing, Fourier and inverse Fourier will be support, as well as all the different variation we have in the system, right? Fourier cosine, discrete cosine, and sine discrete sine, and such. Also, what we hope is to have most of the descriptive statistics available. So right now, mean, variance, standard deviation should work, and obviously sort, mean, max, and different ordering, should work on GPU arrays, right? And all those operations and everything I'm talking about, all those functions I'm talking about now actually running directly on the GPU, right? Up to the level of returning the type setting, which have pretty much a reference to the memory address on the GPU after the operations. So we kind of bypass that data transfer level on both sides. So that was pretty much for statistics. Now, in terms of mathematical function, obviously we want to support all the arithmetic function, plus, time, division, and corresponding total and accumulate, which are derived from those arithmetic functions, trigonometric functions, transcendental, exponential, hyperbolic functions, and so on. So it's a kind of long list, and a few special functions, integral functions, and all the absolute value and sign functions. And as you can imagine, this is a long list, and we put some effort to actually make sure that all those works, right? And I won't dive too much in the details. As you may imagine, there is numerical error happening, there is a failure, none appearing during operation and such. So there is all that framework we are putting in place to control it. But essentially what we are hoping is to make sure that you get the best performance and the full use of your GPU, right? So we have to kind of strike the right balance of spending time verifying that the operation is happening at the right precision, and there is the right failure mode if you have a division by 0 or a result from infinity, and so on. So there's all that work going behind the scene, and we hope to kind of achieve it with time progressively. Okay. So that was in mathematical functions. And so I will just take one question here first. Do you have a rule of thumb for roughly how many arithmetic operations have to be executed on each element of a GPU array for it to be worth the cost of transferring data to the GPU and back to the CPU? That's a great question, and we are actually right now working on it, right? So, but let's say that in most of the case, or at least from what we have seen, it's some basic operation, right? Especially the arithmetic one are, really highly very well implemented, on the CPU side, right? We are using MKL compiler, which, if you are, for example, on Intel compiler, it uses the right, AVX, vector instruction, right? And it actually tap to the CPU and actually get the right performance, right? So what we have noticed, at least I've noticed, in some cases, when you get really to the range of, 10 million or higher, then you kind of start to get close to the, CPU performance, right? And the data transfer, get lower. But for some basic operation, it'd be hard to actually, be faster than the CPU, right? And we probably, at some point actually give all the performance data and what we managed to achieve. And I believe ITA in his talk will kind of show some of those in terms of for linear algebra. What's the performance between the CPU and the GPU? Sorry. In between, sorry, I should, okay, so that's good. So in summary, right? So what we want to introduce is a framework for array computation on the GPU, right? And we want to make sure that, all the core area in the system actually use the GPU, right? Linear algebra, signal processing, graph, image processing, and such. And you can imagine that's a long-term project, right? We want to make sure that we support most of the GPUs, right? We want to make sure that the workflow, there's no failure in between, right? Especially for our high-level function, right? So what happens if you take a GPU array and you put it in the function, which there is no hope to actually be able to have a GPU implementation. So we want to make sure that we hit the right balance, and then you don't get interrupted in your workflow and things actually just working, right? So that's actually all the feature we are trying to put in place so that you just naturally just create an array and it just work for you and you tap the right hardware which is available on your machine. And as I also pointed out, if you really want to go down and work with, CUDA extension and the compiler, then you can actually do that and still have the GPU array around. So that's kind of a brief overview. And as you see, the whole framework relies on just one new object, which is GPU array, right? And it's just to fully integrate it in all parts of the system. So before I close, and I kind of try to answer most of, some of your questions, I want to highlight again, ITA talk at 3, just after this talk. And tomorrow we have office hour around 3 p.m., so around the same time. And feel free to stop by the discrete computation booth. We are there and we'll be happy to answer your question about GPU array, geometry, graph and networks, number theory, and such. And subscribe to our Wolfram R&D channel, YouTube channel. We post update and give presentation about all the latest feature in the Wolfram language. I will go ahead and try to cover some of the questions here. So will you share the notebook? Yes, definitely. I will send that notebook and it should be on very soon. So I'll make sure for that. Bart talk about the font is too small. I'm sorry about that. And hopefully when you get the notebook, you should be able to go to it. So Enrique is asking, how about adjacency matrix from graph? This would be a good direction for this. Yes, definitely. That's kind of one of our next stages. Graph behind the scene is really polymorphic, right? It have a double linked list presentation, you have a sparse array representation, a dense representations, right? Depending on how you build your graph and for efficiency. And our first talk will be, it'll be perfect to support a GPUArray graph, or essentially do all the graph computation on the GPU, right? And we have seen lately, like NVIDIA added cuGraph, which they cover a small set, but it's a good start for centrality on that side. So we hope to do that, right? So definitely that's coming. So a question for Dave. NVIDIA had some tool for executing Python code on GPU called number, SAPI, and RAP. Perfect. Do you have any plan to support these tools from within the Wolfram language? Not directly, right? So, but in short, it'll be exactly, pretty much what GPUArray is doing, right? So if you take, for example, SAPI and, all what NVIDIA have been building, usually when they, in their workflow, right, they have the, CUDA toolkit, right? And then on top, they have several libraries, cuGraph and other library. And then just above it, they have an interface or a wrapper, with Python, right? So in short, GPUArray will be a wrapper for those library and underlying software for NVIDIA. So we'll achieve all that in that one framework. Next question for Kerry is, will any of the GPUArray will be available in 14? Yes, GPUArray will be available in 14, and the list of features I just presented will be those. So linear algebra, statistic, Fourier, discrete Fourier analysis, and mathematical function, and obviously compilations. So that's kind of the start of all that. Okay, so next question from Sasha. Will GPUArray be supported for Apple Silicon? Yes, our hope is to support, all GPU out there. Probably for this first release of GPUArray, we'll have a support on Apple, but limited, right? Not at the same extent as we'll have for NVIDIA CUDA, right? But we hope to actually continuous work and, bring all that to the same level. But yes, we'll have support of GPUArray on Apple. Okay. Well, I think I answered most of the questions. And if you have any more questions, feel free to stop by our booth or to the office hour tomorrow, or just, open a chat, send us an email, and we can continue the discussion. Thank you very much for attending, and have a great conference.